Welcome back. In this section, we're going to start looking at implicitly defined functions and how to find derivatives of implicitly defined functions. Up till now, you've mostly looked at explicitly defined functions, like the ones on the screen, where y is written explicitly as a function of x. So I have y on one side and only things involving x on the other, like y equals 3x squared, or y equals cosine of x plus 7 over x squared plus 1. For both of these, I have y written explicitly as a function of x. I have it just as y equals and only things involving x on the other side. Now, sometimes you'll have a function that'll be written implicitly, in which case I mean we have x's and y's combined together. We don't have it written as y equals something only involving x. So the equation that I've got here, 2xy plus x squared y equals 5, currently that's written implicitly. It's a function, y is a function of x, but here I've got y sort of buried in along with all of these x's. And in some cases, it's possible that you could write it explicitly. For this one, if I'm looking at the function that I have here, I can see that y could be factored out of all of the terms on the left. So that once I've done that, I could rewrite this really as just 5 over x squared plus 2x is my function. And so now I would have it explicitly written as a function of x. Y is now written as y equals. So if I wanted to find the derivative, it wouldn't be too hard for me to do. I could just use the rules that we've learned up till now. Now, unfortunately, not all functions are going to be that way. You'll see functions maybe like this one, where I've got maybe y cubes and y to the fives, and there's even trig functions of y. For an equation like this, there's not really anything you'd be able to do to write it in the form of y equals. So this would be a function where it is implicitly written, and there's not much else we can do about it. So that means for those kind of functions, we're still going to need to talk about how we would deal with taking the derivative of them. But for functions like the one that we saw before, the one where we can write it explicitly, we can find the derivative just using the rules that we've known from the past. So my plan was I was factoring out the x squared and the 2x from the y, and then I wrote it as y equals. And now that I've done that, I can go ahead and find my derivative just by using my derivative rules. Just before I do that, though, I'm going to make a little choice here, and that is you might think about using quotient rule, which is fair enough, because technically you do have a quotient. However, you don't really have a quotient where the numerator and the denominator are both really functions involving x. The numerator is just a constant function. So if I wanted to, I could skip using the quotient rule altogether if I were to first rewrite this as 5 times x squared plus 2x to the minus 1. And then that saves me a little bit of work. The quotient rule is a little bit more involved than just using the chain rule and power rule. And now that I've got it written in this form, when I find the derivative, it's just going to be a matter of using, like I said, chain rule and power rule. So dy dx, I'll leave that constant multiple 5 in the front. And then first, chain rule says I'll be dealing with the power first, then I'll deal with the inside after. Raised to the power of minus 1, power rule says the power will come down, the power will get reduced by 1. Negative 1 minus 1 is negative 2. And so we've only dealt with the outside at that point, which means the inside stays as it is, x squared plus 2x. And then last thing I need to do, just take the derivative of the inside function, derivative of x squared plus 2x. X squared, the derivative is 2x, and 2x, the derivative is 2. And then the last thing I can do is just clean this up a little bit. I have x squared minus x squared plus 2x in the denominator, squared. I have a minus 5 times 2x plus 2. And then maybe the only other thing that I might consider doing is for the 2x plus 2, taking the 2 out as a common factor. So I have really minus 10 times x plus 1 over x squared plus 2x all squared. And there we go. There's my derivative for the function that we had. I found my explicitly written derivative for the function after I wrote it explicitly. Now, implicit differentiation is what we're going to use when we have an equation and we can't write it explicitly. One variable is a function of the other. So what we'll do is we'll take the derivative of both sides of the equation with respect to x. If we're looking for dy dx, then we're taking derivatives with respect to x. And so we'll just have to remember one thing, which is when we take the derivative of something involving x's, then I'm just using my regular derivative rules. But if I'm taking the derivative of something involving y's, I'll have to remember that there's a chain rule involved there because y is a function of x. So in other words, when I'm taking the derivative of just x itself, the derivative is 1. But if I take the derivative of y, it's not 1, it's dy dx because y is a function of x. And so I'm just going to have to keep that in mind as I take the derivatives of all of the terms on both sides of the equation. So here's one that we'll take a look at here. I've got 5x squared plus 2y equals xy, and I want to find the derivative. So I'm going to do this with implicit differentiation. So I'm going to differentiate both sides, and I'm going to differentiate both sides with respect to the variable x. I kind of have to say that because if I don't say in advance who am I considering to be the independent variable, who am I taking derivative with respect to, then the reader won't know. Am I thinking of y being the function or am I thinking of x being the function? So here I'm thinking of x being the variable. We're taking derivatives with respect to x, and so y I'm thinking of that as being a function of x. So in my mind, not that I'm writing it this way, but y is really y of x. So when I take the derivative of y, it won't be 1, it'll be 1 times derivative of y with respect to x. So I'll show you what I mean. We'll work our way from left to right here. For the first term, 5x squared, the derivative of that is just 5 times 2, or 10x, power reduced by 1, power is 1. So I've just used power rule there. For 2 times y, 2 is a constant multiple, so I'll leave that in front. And the derivative of y is dy dx. On the right side of the equation, I have x times y. So that's a product, which means I'll need to use product rule. First thing as it is, which is x, times derivative of the second thing, derivative of y, which is dy dx, plus the second thing as it is, times derivative of the first. Derivative of x is 1. And now I'm just going to do a little bit of cleaning up here. I'm going to bring everybody with dy dx to one side of the equation. So I'll bring everybody to the right side. So x dy dx minus 2 dy dx. And I'll bring everybody else to the other side of the equation, the 10x minus y. So now I can factor out dy dx on the right side. And I can go ahead and solve for dy dx by dividing both sides by x minus 2. Okay, so we found our derivative. I have about 2 or 3 little things to say about this. So one of them is first addressing the question itself. It asked us to find the derivative and then also talk about where is this function differentiable. So if I'm looking at the derivative that I have down below, I can see that this is not defined if x is 2. So it's not differentiable at x being 2. The derivative doesn't exist there. So everywhere else the function is differentiable. That's number one. Number two, you might have noticed if we started off with an implicitly written equation, then we wind up with a derivative that's also implicitly written. That's usually the case. We had x's and y's mixed up together in the equation, and you'll notice in the derivative we have x's and y's. So if I wanted to know what is dy dx, I wouldn't need to know just the value of x that I'm interested in, but I'd also need to know the value of y that's for the point that's on that curve. If you're thinking about this, you could have tackled this problem in a different way. You might have noticed if you took a look at the equation that it could be written implicitly. So I could have taken it and started off by first bringing the 2y to the other side, then factoring out the y, and then solving. And I guess this also makes it a little bit more obvious as to why our function doesn't have a derivative when x equals 2, and that's because the function has a vertical asymptote when x is equal to 2. If we wanted to, we could take our derivative dy dx of this function, and of course, since it's an explicitly written equation, we'd wind up getting a derivative that's explicitly written as well. So sometimes you'll have more than one option available to you. If it's worth your while to write something explicitly to save yourself a few minutes taking a derivative, then maybe go ahead. Of course, it's not always going to be possible for you to do that. Okay, here's another one. This one is one where, again, it's possible for us to write it explicitly. So if you're thinking about the equation that we have, x is equal to tangent y, I could rewrite this explicitly as tangent inverse of x is equal to y. So in other words, what I'm really asking us to find in this equation is what is the derivative of tangent inverse, which of course you currently do not know what that derivative is. We haven't even talked about inverse trig functions at all in this course yet. So interestingly enough, though, even though we haven't talked about finding the derivative of tangent inverse, we actually can now, simply by rewriting it as x equals tangent of y and then using implicit differentiation. So here, even though I could write it explicitly as y equals tangent inverse of x, that wouldn't really help me for finding dy dx since I don't know the derivative of tangent inverse. But I do know the derivative of tangent, so I'm going to differentiate both sides with respect to x. So on the left side, the derivative of x, that would be 1. On the right side, I have here a chain rule moment because I have tangent as the outer function and y is the inner function. So derivative of tangent, I know that that is secant squared. And the inner function, the derivative of y, well, that's dy dx. So I could rewrite this as the derivative is 1 over secant squared of y, or if I felt like it, I could go one step further maybe and say it's 1 over secant squared is the same thing as cosine squared of y. And all of that's lovely, but again, one of the problems that we have is if you were interested in a particular value of x for dy dx, unfortunately, x doesn't show up in dy dx at all. You might want to say, well, we have an implicitly written derivative. Is there any way for us to come up with an explicitly written derivative? And there is. So here, let's just do a little bit of work on the side. One thing that we said at the very beginning, our equation that we were starting with, was x is equal to tangent of y. And I know for my derivative is in terms of either cosine squareds of y or secant squareds of y. And I happen to know, of course, there's a relationship between tangent and secant, and that's our Pythagorean identity. Secant squared is tangent squared plus 1. So I'm going to start with the equation x is equal to tangent of y, square both sides, so x squared is tangent squared y. I'll add 1 to both sides. So I have x squared plus 1 and tangent squared y plus 1. And because of my Pythagorean identity, tangent squared y plus 1 is equal to secant squared y And so now I'm pretty much good to go because I now can say I had that the derivative was 1 over secant squared y. So since the derivative is 1 over secant squared y, and secant squared y is x squared plus 1, so explicitly written, the derivative is 1 over x squared plus 1. So as a fun little twist here, we started really off, the real question was find the derivative of tangent inverse, and we've now found the explicit derivative. It is 1 over x squared plus 1. Okay, so same thing as before, nothing really new here. The derivative dy dx is still giving us the slope of our tangent line. So if you have an equation and I ask you to find the tangent line, you're still going to do the same things. Find the derivative, use the derivative to find the slope at whatever point we're interested in, then use the slope and use the point to find the equation of the line. So here, conveniently enough, the point, we completely have that. 3, 3, we don't even need to find out what the y value is for our point because we've been told it's 3. So the only thing we need is to find our slope, and for our slope, we need to find the derivative. So again, we're going to differentiate both sides with respect to x. And so starting with the left side, I have x cubed. The derivative is 3x squared. For y cubed, it's 3y squared. And of course, chain rule, y is a function, so the derivative of y itself is dy dx. And then next up, we have minus 6xy. So I'm going to think about that as a product. The minus 6x is the first part, and the y being the second part. So product rule says first thing as it is, so minus 6x times the derivative of the second thing. Derivative of y is dy dx, plus the second thing as it is, y, times the derivative of the first thing. Derivative of minus 6x is minus 6. And on the right side, it's equal to 0, and the derivative of 0 is 0. Of course, don't forget that whenever we're doing implicit differentiation, there's two sides of the equation, so we have to remember to take derivatives of both sides. So now, next thing I'm going to do, I'm not going to really bother to simplify this because we're going to find out what our derivative is at 3, 3. So really what I'm going to do next is just put in 3 for x and 3 for y, and then that'll make things a little faster for me. So when I put in 3 for x and 3 for y, I've got 27 plus 27 dy dx minus 18 dy dx minus 18 equals 0. And then after I do a little bit of cleaning up, I will have 9 dy dx. And if I move the 27 and the minus 18 to the other side, it gives me minus 9. So it looks like my slope is negative 1. And so now we can come up with our equation of our tangent line. So y minus the y coordinate equals our slope times x minus our x coordinate. And the y value for our point is 3. The slope is negative 1. And the x coordinate is 3. And then just a little bit of cleaning things up, and then we're finished. So I have y equals negative x plus 6, or y equals 6 minus x, as the equation of my tangent line.